The Integrated Electronic Standby System, IESS, permits the computation and the display of the three main functions, should the main instruments fail: attitude, pitch and roll, standard or barometric corrected altitude, and associated barometric pressure, indicated airspeed. In addition, the IESS provides the following secondary functions or displays: indicated Mach number, VMO, MMO, slip skid indication, vertical speed, ILS, barometric pressure in hectopascal, and altitude in meters. The IESS relies on 28-volt DC power provided by the DC Essential Buses 1 and 2. In case of an electrical emergency, it will continue to operate powered by the ram air turbine or by the batteries through the Essential DC Bus 2. The system is powered as soon as battery 1 is switched to on and battery 2 is switched to auto. Then, the IESS starts its alignment phase, which requires about 90 seconds to be completed, and can be identified on the screen by its alignment flag. Note, the airplane must not be moved during the first 90 seconds after power-up, while the IESS is undergoing alignment. Moving the airplane during this period can cause in-flight attitude indication errors that are not noticeable on ground. Attitude, using the data from the respective sensors after its conversion to digital format, the system computes and displays attitude. The cage button resets attitude to provide a fast erect function. This function is not operational during the initialization mode and must only be used in stabilized flight conditions. Altitude data is provided by processing static pressure sensed by ADS-B 3 and 4. Altitude is displayed in tape format. Pushing the Standard button sets the IESS reference barometric pressure to standard, Q and E. Barometric pressure can be adjusted, starting from the standard value, by using the rotary baro knob. Indicated airspeed data is presented in tape format and is provided by processing dynamic pressure sensed by ADS-B 3. In case of abnormal operation or failure detection by the internal monitoring in one or several IESS functions, the following flags are displayed: attitude, altitude, airspeed, vertical speed, and ILS. For example, if the ILS discrete label is not received or not valid, the 2 pointers and the associated scales are removed with red cross failure displayed and ILS-1 displayed in amber. If the receiver is not tuned on the ILS frequency, the 2 pointers and the associated scales are removed without the display of red cross failure. Any other indication that fails will be blanked and covered by a red cross. The Air Data System, ADS, provides primary air data information to primary flight displays, flight controls, and other avionics as required. The pressure sensing elements of the Air Data Computer, ADC, are mounted in the Air Data Smart Probes, ADSP, and sense total pressure, static pressure, local angle of attack, AOA, and total air temperature, TAT. These parameters are sent to the Air Data Application, ADA, hosted on a Digital Engine Operating System, DEOS, platform in the Modular Avionics Unit, MAU. The ADSPs are located on the nose of the airplane. ADSPs 1 and 2 are symmetrically located and are further forward and lower on the nose than the symmetrically located ADSPs 3 and 4. Total air temperature probes 1 and 2 are symmetrically located. The ADC performs air data pressure calculations, which are forwarded to the Air Data Application resident in MAU, or to the Integrated Electronic Standby System, for airplane fuselage effects and sends the information to the flight deck to be displayed as airspeed, altitude, Mach, and angle of attack. The ADA corrects the local air data values received from the air data system. This air data information is also sent to airplane systems that require air data input, such as stall protection, flight controls, and others. The Micro Inertial Reference Unit, IRU, uses air data to calculate wind-related parameters. During normal operation, air data readouts on the captain and first officer's PFDs are from ADS-1 and ADS-2, respectively. Upon failure of either ADS-1 or 2, only the affected side will lose the ADS readout, and a failure indication will be provided to the flight crew. The affected side will automatically revert to ADS-3. In addition, the pilot can select one of the two remaining ADSs for the associated PFD's air data display. For one or two ADS failures, the reversionary logic for the captain and first officer PFDs can be seen in the following table. The Air Data Smart Probe, ADS-P, combines pitot, static, angle of attack, and some air data computer functions into a dual-channel unit. It consists of an air data computer attached to a multifunction probe. The MFP utilizes a single heater element to ensure that the probe strut and head remain free of ice. The ADC monitors the probe current to detect any heater failures and actively controls the heater temperature. The ADC is physically and pneumatically connected to the MFP. The MFP is a one-piece probe that contains a total pressure port, 2 alpha pressure ports, and 2 drain holes. Each port is paired to a pressure sensor located in the ADC. 2 absolute pressure sensors measure pressure data from the total pressure port and the alpha port. A differential pressure sensor measures the difference between the pressure data from the alpha pressure ports. From the 3 measured pressures, the local total pressure, local static pressure, and local angle of attack are computed. The magnetic standby compass is a single, independent unit mounted on the center windshield structure, below the overhead panel. It is used as a standby heading source. The compass has no system interface, but receives power for illumination via the 28-volt DC Essential Bus 1. Illumination of the compass is controlled by the standby clock dim control on the co-pilot's lighting control panel. The standby clock dim control also controls illumination brightness for the clock and integrated electronic standby system. Inertial Reference System, IRS. The IRS provides the pilots with accurate and dependable attitude, heading, and position information to aid in navigation. The main component of the IRS is the Micro Inertial Reference Unit, IRU. The Micro IRU differs from previous generations of IRUs mainly due to the addition of the following features: Align in Motion capability, automatic mode control logic, which eliminates the need for a mode control unit, electronic tray alignment. The IRS interfaces with the airplane systems and equipment to receive input data from Modular Avionics Unit, MAU, generic input-output modules. The IR component requires initialization, entry of latitude and longitude from the FMS or GPS, or it may be entered manually. Modular Avionics Module, MAU, GPS modules. Aircraft Personality Module, APM, dedicated to each IRU, to read and write stored data, serial number, alignment, and performance parameters, etc. Air Data Computer, ADC. Information such as altitude, altitude rate, and true airspeed are received in order to correct output to other avionics systems. In addition, the IRS interfaces with the following airplane systems and equipment to transmit inertial output data: Modular Avionics Unit, generic I/O modules for the electronic display systems, and is displayed to the crew on the PFDs. Modular Avionics Unit, generic I/O modules for the weather radar system. Modular Avionics Unit, AFCS I/O modules. The AFCS receives accelerations, attitudes, and attitudes rates data from IRS. Air Data Smart Probe. The ADSP receives inertial data to perform slip static pressure compensation. Flight Management System. The FMS receives the positional information in order to display the alignment status of the IRS on the MCDU IRU status page. Integrated Standby System. Inertial Reference System Components. Each IRS consists of 2 micro-inertial reference units, 2 mounting trays, and 2 aircraft personality modules. The micro-IRU can operate from either a primary input 28-volt DC power source or a secondary input power source, with priority being given to the primary power source if both primary and secondary sources are available and valid. The primary and secondary input power for micro IRU1 are Essential Bus 1 and Essential Bus 2, respectively. The primary and secondary input power for micro IRU2 is DC Bus 2 and DC Bus 1, respectively. In an electrical emergency configuration, the IRS-1 will remain operating powered by the ram air turbine generator. Inertial Reference, IR. The inertial reference component of the micro-IRU contains 3 accelerometers and 3 ring laser gyros. The accelerometers measure linear motion along the longitudinal, lateral, and vertical axes. The ring laser gyros measure angular motion about the longitudinal, lateral, and vertical axes. These sensors, coupled with high-speed microprocessors, allow the IRUs to maintain a stable platform. The IRUs are located in the forward electronics compartment. Micro IRS Aircraft Personality Module Unit, APM. The APM is programmed to contain configuration and installation data. This data facilitates storage of configuration, selects, and data regarding the tray alignment electronically. The APM is initially programmed as a part of the tray alignment procedure. The configuration may be changed later without modifying the installation data. IRS Operating Modes. The Micro IRU has the following operational modes: Power Up, Alignment, Stationary Alignment, Align in Motion, Auto Realign, Navigation, Attitude, Reversionary, Align in Motion, End of Flight. Control of the modes is fully automatic, which means that no input is required from the flight crew to select or enter a mode. Power-up mode. The IRU will initiate a normal power-up when the IRU is energized, or a warm start power-up when an IRU reset command is issued. The warm start power-up allows for a faster attitude output recovery following power interrupts that exceed the power hold-up capability of the IRU. In both cases, a built-in test is performed during the power-up. The built-in test performs a check of IRU internal operation and external interfaces and consists of the following 3 types of tests. The power-up test is performed during the power-up mode and 1 time during the alignment, or when the micro IRU mode changes from the alignment mode to navigation mode. The alignment tests are done only during the alignment modes. The continuous tests are done at regular times as long as the IRU is energized. Alignment mode. The micro IRU automatically selects the correct alignment mode. The two possible modes are stationary align. The stationary alignment mode is the primary method of alignment. This mode is selected when the aircraft is on the ground and not moving. The time required to complete a stationary alignment varies with latitude, ranging from 5 to 17 minutes. The alignment may fail if the micro IRU senses excessive motion during the initialization sequence, or if the micro IRU fails to receive an initialization position. A position may be obtained from the FMS, GPS, or entered by the flight crew. Align in motion. The AIM mode initializes the IRS while in flight to recover full IRU navigation capability. This mode will be selected in the event of a power loss while in flight. The time required to complete an AIM varies as a function of airplane motion and ranges from 15 to 30 minutes. When the micro IRU is performing an AIM, the flight crew will be notified by an appropriate ICAS message. Stationary alignment and AIM modes are performed in conjunction with the attitude mode prior to entry into the navigation mode. In order to perform an AIM, the IRU requires GPS valid data. Should the AIM fail, the micro IRU will remain in attitude mode, with attitude data available but with positional data unavailable. Auto Realign Mode. The Auto Realign mode is performed in conjunction with the navigation mode when the airplane is stationary to maintain optimal performance and automatically realigns the micro IRU between flights. Navigation mode. When the IRS enters into the navigation mode, it will remain in this mode until the system is turned off. Attitude mode. The primary function of the attitude mode is to rapidly establish pitch and roll attitudes after completion of the power-up mode. Attitude mode runs concurrently with the alignment modes, either stationary or alignment in motion. Reversionary attitude mode. This mode operates in conjunction with the stationary alignment mode. The IRS automatically enters the reversionary attitude mode after completion of the power-up mode. Align in motion attitude mode. This mode, also known as attitude mode, operates in conjunction with the align in motion mode. This mode provides attitude and heading performance. End of flight mode. This mode is performed in conjunction with the navigation mode. The micro IRU automatically enters this mode after landing when the airplane has been motionless for a period of 5 seconds. The end of flight mode stores navigation performance records, auto-calibration data, and other miscellaneous information after each flight. IRS operation. Initialization. The position initialization is automatically transmitted by the Global Positioning System, GPS. The position initialization may be manually entered via the MCDU, FMS. Push the nav function key to display the navigation index page on the MCDU. Select the position initialization prompt from either the identification or position sensors page. Position initialization page lists positions that can be line selected for initialization of the FMS using the load prompt. IRS abnormal operation. In the event of a normal aircraft power interrupt or power transient, no degradation in performance will occur due to the switching or operating from the backup power source. The two micro IRUs receive power from different primary and different secondary power sources. So, in the event of a loss of power to one micro IRU, the other micro IRU would not also experience a power loss at the same time. If both micro-IRUs fail or suffer a loss of power simultaneously, an appropriate ICUS message will be issued and the flight crew will have to use the remaining navigation instruments and systems. Reversionary mode. The IRS switch on the reversionary panel changes the attitude and heading source from the on-side IRS to the cross-side IRS. If the reversionary mode is selected, the FD modes disengage. The AP modes disengage. FD-AP can be re-engaged after the previous disengagement. The enunciation changes accordingly. IRS-1 or IRS-2. Comparison monitor. The comparison monitor detects a miscomparison between IRS-1 and 2, pitch, roll, and heading data. When data miscompare is beyond limits, the enunciation is displayed. The following ICUS messages will be displayed in the cockpit. The radar altimeter system provides accurate absolute altitude above terrain, decision height enunciation, and low altitude awareness up to 2,500 feet above ground level. One radar altimeter system is the standard system, and a second system is optional. The radar altimeter system 1 is powered by the DC bus 1, and the system 2, if installed, is powered by the DC bus 2. In a single system installation, the same radar altitude is displayed in both PFDs as a digital readout. In a dual system installation, PFD-1 displays System 1 radar altitude, and PFD-2 displays System 2 radar altitude. The system interfaces with the TCAS, which uses the radar altitude information to inhibit descend resolution advisories. The system also interfaces with the MAU for data distribution and integrity checking. In addition, other interfaces are performed, such as with the EGPWS system to determine airplane sync rate variation, with the DVDR system in order to record mandatory parameters. When one or both of the radio altimeters has failed, the associated CAS message, radio altimeter 1 fail, or radio altimeter 2 fail, is displayed on the ICUS display. VHF Omnidirectional Radio and Instrument Landing, VHF NAV. The VHF navigation system enables VOR and ADF en route flight phase navigation, terminal area navigation, and aircraft approach landing phase navigation guidance, using localizer, glide slope, and marker beacon distance to runway threshold information. The receiver system automatically pairs localizer and glide slope channels to assigned frequencies. The VHF NAV system consists of 2 NAV modules, one in each MRC, one dual GS antenna, one marker beacon antenna with a duplexer, one dual VOR localizer antenna, one per NAV module. Press Radio button on the MCDU to go to radio page 1 of 2. On radio page 1 of 2, it is possible to tune and activate the ILS VOR frequency. The tuning can be accomplished using the tuning knob or the numeric buttons. If the tuning knob is used, the standby frequency must be boxed prior to pressing its respective line select key. If using the numeric keys, enter the standby frequency and press the respective line select key. To activate the standby frequency, press the respective active frequency. Press the respective standby frequency twice if not boxed, otherwise press once to go to NAV page 1 of 1. On the NAV page 1 of 1 is possible to capture a frequency tuned in memory. Press the respective line select key to box the memory tune and use the tuning knob to cycle the stored frequencies. Press the active frequency to capture the selected memory tune. Press the line select key next to FMS to cycle FMS Tune Enable or Disable. Press the line select key next to DME to cycle DME hold on or off. The Enhanced Ground Proximity Warning System, EGPWS, uses airplane position, configuration, and terrain database information to provide the flight crew with increased awareness of the terrain along the projected flight path. The system provides the flight crew with sufficient information and alerting to detect a potentially hazardous terrain situation and thus allow the flight crew to take effective action to prevent a controlled flight into terrain event. The EGPWS is a module contained in the Modular Avionics Unit, MAU number 2, and it is powered via Essential DC Bus number 2. The EGPWS receives inputs from the following systems: Air Data System, ADS, Flight Management System, FMS, Global Positioning System, GPS, Inertial Reference System, IRS, Radar Altimeter, Slats and Flaps Control System. The Terrain Clearance Floor, TCF, provides a circular terrain clearance envelope around the airport runway, alerting the pilot of a possible premature descent for non-precision approaches regardless of the airplane's configuration. The TCF is active during takeoff, cruise, and final approach, and is based on current airplane position, nearest runway, and radio altitude. The database consists of all hard surface runways of the world, greater than 1,067 meters, 3,500 feet in length, which have a published instrument approach procedure. The EGPWS has 6 different modes of operation. Mode 1. The excessive descent rate.
Sink rate, pull up, pull up, pull up.
Mode 2. The excessive closure to terrain.
Terrain, pull up, pull up, pull up.
Mode 3. The altitude loss after takeoff.
Don't sink, don't sink.
Mode 4. The unsafe terrain clearance. It generates 3 types of aural alerts based on radar altitude, airspeed, and airplane configuration.
Too low. Terrain. Too low. Gear. Too low. Terrain. Too low. Flaps. Too low. Terrain.
Mode 5. The descent below glide slope.
Glide slope. Glide slope. Glide slope.
Mode 6. The altitude callouts.
500. Approaching minimums. 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 200.
Bank angle callouts.
Bank angle. Bank angle.
Mode 1. The excessive descent rate.
Sink rate. Pull up, pull up, pull up.
The EGPWS terrain display is designed to increase flight crew awareness of the surrounding terrain in varying density dot patterns which represent specific terrain separation with respect to the airplane. Solid yellow is caution terrain, approximately 60 seconds from impact. Solid red is warning terrain, approximately 30 seconds from impact. High-density red dots is for terrain that is more than 2,000 feet above airplane altitude. High-density yellow dots is for terrain that is between 1,000 and 2,000 feet above airplane altitude. Low-density yellow dots is for terrain that is between 500 feet, 250 feet with gear down, below, and 1,000 feet above airplane altitude. High-density green dots is for terrain that is the middle elevation band when there is no red or yellow terrain areas within range on the display. Low-density green dots is for terrain that is the lower elevation band when there is no red or yellow terrain areas within range on the display. Light-density cyan dots is for terrain elevation equal to 0 feet MSL. In the event of a failure, the EGPWS will generate a message to alert the flight crew. The system uses a dedicated terrain display bus from the EGPWS to present terrain data. If the terrain picture bus has failed, the entire terrain picture is cleared and an amber terrain annunciation is presented. The MFD terrain annunciation is as follows. The labels and its functions are: a green terrain is lit when terrain mode is selected. An amber terrain fail is lit when a failure condition exists. A white terrain inhibit is lit when the terrain inhibit button is pressed in approach mode. An amber terrain in-A is lit when EGPWS is uncertain of the airplane's position. A white terrain test is lit when the self-test is activated. Some buttons in the cockpit allow pilots to interact with the EGPWS. They are the EGPWS Terrain System Inhibit button. When pressed, in approach mode, it inhibits EGPWS and avoids unwanted terrain alerts in airports not covered by EGPWS database. The EGPWS Glide Slope Inhibit button. The momentary action button annunciator is used to manually cancel glide slope alerts. It illuminates when pressed anytime the aircraft is below 2,000 feet radar altitude and will be automatically reset, light is off, by climbing above 2,000 feet or descending below 30 feet. The flap override switch, guarded, inhibits triggering flap alerts in case of landings in which flap configuration is different from flap landing configuration. Dangerous shear winds can result from vertical winds and rapidly changing horizontal winds. Therefore, special shear wind advisories have to be given to the pilots. Wind shear warning alerts are given for decreasing headwind, increasing tailwind, and severe vertical downdrafts. Wind shear caution alerts are given for increasing headwind and severe updrafts. The wind shear system is part of the Flight Guidance Control System and Enhanced Ground Proximity Warning System. The EGPWS provides the detection portion of the wind shear system, and the FGCS provides the guidance portion. Wind shear detection is only active between 10 and 1,500 feet radio altitude during the initial takeoff, go-around, and final approach phases of flight, and when detected by the EGPWS. Wind shear caution messages include amber wind shear message on the PFD and a single
Caution, wind shear.
aural alert. A wind shear warning message consists of a red wind shear message on the PFD and a single
Wind shear, wind shear, wind shear.
aural alert. The wind shear escape guidance mode provides a pitch command to recover from a wind shear to minimize altitude and airspeed loss during a wind shear encounter.
Caution. Wind shear. Wind shear. Wind shear. Wind shear.
This mode is a flight director mode, and it is engaged either manually by pressing the go-around button while a wind shear condition is detected, or automatically by operating in go-around or take-off mode, or when thrust lever's position is above 70 degrees and a wind shear condition is detected. In this condition, all the other flight director modes are cancelled, and the altitude pre-select, go-around, and take-off modes are inhibited while in a caution or warning wind shear condition. No lateral mode is inhibited while in wind shear mode. The wind shear escape guidance mode incorporates three control logics. The gamma submode. The airplane has a positive flight path angle. This submode allows the airspeed to build up during an increasing performance wind shear in anticipation of a decreasing performance wind shear. The alpha submode. The airplane maintains airspeed when approaching stall conditions. The wind shear protection control logic keeps the airplane angle of attack below the stick shaker firing angle. The speed target submode. The airplane manages the airspeed to prevent overspeed. Pitch up is commanded to maintain the calculated airspeed. Note: wind shear conditions will not be detected if either EGPWS or the radar altimeter is unavailable. All EGPWS warning functions, including the wind shear warning function, are tested during cockpit self-test prior to takeoff. The self-test is activated using the MCDU test page. During the test, an amber wind shear fail message is displayed on the ICUS. A red wind shear message is displayed on the PFD, and a
Wind shear, wind shear, wind shear.
aural message is enunciated. If the wind shear warning function of the EGPWS is inoperative during the test, a wind shear inop aural message is enunciated. Weather radar system. The airplane can be equipped with WU-660 or WU-880 weather radar system models. The weather radar system is designed for detection and analysis of the weather during flight. The weather radar system consists of an integrated receiver, transmitter, antenna unit, RTA, and two virtual weather radar controllers. The RTA is mounted in the nose of the airplane, whereas the virtual controllers consist of the CCDs and the weather mode information displayed on the MFDs below the weather information. The weather radar system is powered by 28-volt DC from SPDA1 DC bus 1. Should a power supply failure occur, the weather radar system will be inoperative, as there is no backup power source for this system. Display of weather data is available on the MFDs and PFDs. Selection of weather data display is accomplished via MFD using a soft key to select Map menu. Selecting Weather from this menu will display the weather information and virtual controller on the MFD. When the weather option is selected on the Map menu following a cold start, the weather information will be displayed. Weather will initially display in a default off mode. Off is the initial active mode selected on the virtual controller. After 45 seconds, when power-up is completed, the pilot can select another available mode using the virtual controller. Functions are displayed in the virtual controller in white, if available, when a specific weather radar mode is selected, and displayed in gray if not available for the selected weather radar mode. Only one of the modes, Weather, GMAP, Standby, and Off, can be selected at one time. Availability of other functions will depend on which of these four modes is selected, and if the airplane is in the air or on the ground. The Weather mode is used to detect areas of severe weather. This will allow the pilots to avoid areas of dangerous weather conditions and possible turbulence. Selecting Weather activates the weather mode and deselects the previous mode. Ground Mapping Mode, GMAP. This mode is used to alert the flight crew about hazards caused by ground targets. This is especially useful in areas of rapidly changing terrain, such as hilly and mountainous areas. Therefore, the selection of preset gain will generally provide the desired mapping display. However, the pilot flying may desire to manually decrease the gain. It is possible to have the pilot working the GMAP mode while the other pilot is using the regular weather mode. Off mode. Selecting this mode turns the radar off, provided Off is selected on both virtual controllers. The system is no longer radiating power and the antenna is stowed. Slave mode. Slave indicates that one controller is in the off position while the other one is in control of both sweeps. Slave indicates that one controller is in the off position while the other one is in control of both sweeps. To select the weather radar menu for display on MFD2, it is necessary to first select the MFD by pushing the center button on CCD2 to display the cursor on MFD2. The touchpad on CCD2 is used to move the cursor to the weather soft key. Pushing one of the Enter keys on CCD2 selects Weather Radar menu for displaying on MFD2. The touchpad on CCD2 will move the cursor to the GMAP circular button on the MFD virtual controller. Then, pushing the Enter key on CCD2 will select it. The touchpad on CCD1 moves the cursor to the Off soft key. Pushing one of the Enter keys on CCD1 selects Weather Radar Off. The Weather Radar menu Slave Annunciator will be lighted on MFD1. Weather Radar Operating Functions. The radar processes return signals in order to determine if a turbulence signature is present. Turb may only be engaged in the weather mode and at selected ranges of 50 nautical miles or less. Range. The range function is controlled via the outer knob on the CCD and can be set to 10, 25, 50, 100, 200, or 300 nautical mile ranges. Note, this function is available only for WU-880 model. The gain control varies the RTA receiver gain. There are two gain modes, variable and calibrated. The preset calibrated mode is the normal mode and is used for weather avoidance. The system will be forced into calibrated gain when RCT or TGT are selected. The variable gain mode is useful for additional weather analysis and for ground mapping. In weather mode, variable gain can increase receiver sensitivity over the calibrated level to show weak targets, or it can be reduced below the calibrated level to eliminate weak returns. Target Alert monitors for red or magenta weather beyond the selected range and 7.5 degrees on each side of the aircraft heading. If such weather is detected within the monitored heading outside the selected range, the Target Alert annunciation changes from a green armed condition to an amber alert condition on the MFD. This annunciation advises the flight crew that potentially hazardous weather lie directly in front and outside of the selected range. When this warning is received, the flight crew should select longer ranges to view the questionable target. The Target Alert is inactive within the selected range. Selecting Target Alert forces the system to preset gain and turns off variable gain mode. The normal radar sweep is plus or minus 60 degrees from the aircraft nose at a rate of 12 sweeps per minute. Selecting the SECT push button reduces the angle of sweep to plus or minus 30 degrees and increases the sweep rate to 24 sweeps per minute. The inner knob on the CCD provides tilt control and gives the pilot manual control of the antenna tilt angle. The CCD inner knob is a dedicated tilt knob if variable gain is not active. Tilt can be varied between 15 degrees up and 15 degrees down. Clockwise rotation tilts beam upward to plus 15 degrees, and counterclockwise rotation tilts beam downward to minus 15 degrees. The tilt control knob also provides the flight crew with the ability to place elevation control under altitude compensated tilt, ACT, which adjusts the antenna tilt in relation to the altitude and selected range, and it is only available for WU-880 model. The tilt knob can be used for fixed offset corrections of up to 2.0 degrees. The React function permits the radar receiver to automatically adjust sensitivity to compensate for attenuation losses as the radar pulse passes through weather targets on its way to illuminate other targets. The React compensation is active in all modes except ground mapping mode. The cyan field indicates areas where further compensation is not possible. This is a warning indication that attenuation is hiding possibly severe weather and should be considered very dangerous. Test. The test function is selected on the Multifunction Control Display Unit, MCDU, avionics test page. The test is used to select a special test pattern to allow verification of system operation. The Traffic Alert and Collision Avoidance System, TCAS, is an independent airborne system which does not rely on air traffic control for control or coordination. It detects unsafe traffic conflicts with other transponder-equipped aircraft and assists the flight crew in avoiding intruders inside a protected airspace. This is accomplished by interrogating the Mode A, Mode C, and Mode S transponders, tracking responses, and providing advisories to the flight crew of the vertical separation from intruders. There are two levels of advisories. TAs. Traffic advisories indicate the range, bearing, and relative altitude of the intruder to aid in visual acquisition of the intruder. A traffic advisory is defined as an intruder aircraft entering the caution area 35 to 45 seconds from the TCAS collision area. Note: a visual search is recommended to prepare for intruder avoidance. RAs. Resolution advisories indicate what vertical maneuver must be performed or avoided to assure safe separation. A resolution advisory is given for an intruder aircraft entering the warning area 20 to 30 seconds from the TCAS collision area. Note, prompt action is required to avoid the intruder. If the intruding aircraft is also equipped with TCAS, the two systems can communicate their mutual intentions for an avoidance maneuver through the Mode S transponders. Mode A transponder-equipped intruders result in detection and display of traffic advisories only. Intruders not equipped with a transponder are invisible to the TCAS. The TCAS consists of the following components and associated controls. A directional antenna, located on top of the aircraft. An omnidirectional antenna, located on the bottom of the aircraft. The TCAS computer is mounted in the forward avionics bay. In the cockpit, the TCAS modes are selected through the MCDU, and the TCAS functions are selected on the multifunction display by the cursor control device. The CCD and the multifunction display together make up the TCAS virtual controller. To select the radio page, first push the radio function key on the MCDU. From there, push the line select key next to the TCAS transponder label in order to access the TCAS transponder page. The line select key 1L shows the TCAS and transponder modes. To select the desired mode, this select key has to be pressed as required until the desired mode is displayed in green. The modes are mutually exclusive. Leaving the detail page is self-explanatory. Note, on the radio page, pushing the lower left line select key allows toggling between standby and the previously selected TCAS transponder mode. Two mutually exclusive display formats are available on the MFD: a TCAS map overlay format and a TCAS zoom format. To access them, operate the CCD as follows. Push the respective format location button to select the MFD. Via the touchpad, position the cursor to the map soft key and open the pull-down menu by pushing the Enter button. Selecting the TCAS checkbox overlays the TCAS format onto the map format and displays the TCAS data box in the top half of the MFD. With the TCAS checkbox not selected, the TCAS zoom format is displayed in the bottom half of the MFD. Push the TCAS soft key to open the TCAS virtual controller, and then use the CCD to operate its controls. Note, all selections on the TCAS virtual controller apply to both formats. The mode selected via the MCDU is also displayed on the MFD. For the overlay format, the mode is displayed in the TCAS data box. For the zoom format, it is shown on the right side of the display. The following TCAS mode enunciations are displayed on the PFD. TCAS off indicates TCAS off and also indicates standby. TCAS test indicates functional test. TCAS fail indicates TCAS system failure. TA only indicates traffic advisory only mode. TCAS RA fail indicates resolution advisory mode failure. TARA indicates a valid indication that the computer is in TARA mode. The TCAS modes use color-coded symbols and data tags to map air traffic and locate threat aircraft on the two display formats. The symbols are explained as follows. A solid red square represents a resolution advisory, RA. A resolution advisory is given for an intruder aircraft entering the warning area 20 to 30 seconds from the TCAS collision area. A solid amber circle is used for a traffic advisory, TA. A traffic advisory is defined as an intruder aircraft entering the caution area 35 to 45 seconds from the TCAS collision area. A solid cyan diamond stands for proximate traffic, PT. Proximate traffic are aircraft within a range of 6.5 nautical miles and plus or minus 1,200 vertical feet. A hollow cyan diamond symbolizes other traffic, OT. OT can be any transponder replying aircraft not classified as an intruder or proximate traffic and within plus or minus 2,700 feet vertically and within the range of the display. Display of other traffic is inhibited during traffic advisories and resolution advisory. Note, each type of advisory is accompanied by a corresponding oral message generated by the TCAS computer and announced via the flight deck speakers.
Traffic. Traffic.
A data tag gives more detailed information about a threat aircraft. It always appears in the same color as the advisory. On the virtual controller, when relative altitude mode is selected, a 2-digit number displays the relative altitude difference in hundreds of feet. In absolute altitude mode, a 3-digit number displays the flight level. A positive altitude is then displayed with 3 digits, but a negative altitude is displayed with 2 digits followed by a negative sign. When the number is placed above the traffic symbol and preceded by a plus sign, it represents an intruder above the TCAS aircraft. Placed below the traffic symbol and preceded by a minus sign, it represents an intruder below it. Note, absolute altitude is replaced with relative altitude whenever a resolution advisory or traffic advisory condition is encountered. A vertical up arrow will be placed to the immediate right of the traffic symbol if the intruder is climbing in excess of 550 feet per minute. A down arrow represents an intruder descending in excess of 550 feet per minute. Traffic advisories and resolution advisories are always displayed on TCAS map overlay or TCAS zoom formats.
Traffic. Traffic.
When the TCAS detects an RA condition where certain ranges of vertical speed are not recommended, preventive RA, one red trapezoidal avoidance zone is displayed. When the TCAS detects an RA condition and a maneuver is recommended to increase the vertical separation, corrective RA,
Descend. Descend. Descend.
1 or 2 red trapezoidal avoidance zones and a green rectangular fly-to zone are displayed. For any resolution advisory condition, the flight director bars are removed and the flight path angle will become red when it is within the avoidance zone, otherwise it remains green. The resolution advisories are also displayed on vertical speed indicator. The following warning inhibits should apply automatically for TCAS operation. No increased descent commands are issued at altitudes less than 1,450 feet above ground level, when aircraft is descending, or at altitudes less than 1,650 feet when aircraft is climbing. No descent commands are issued at altitudes less than 1,000 feet when the aircraft is descending, or at altitudes less than 1,200 feet when the aircraft is climbing. No resolution advisories are issued at altitudes less than 900 feet when the aircraft is descending, or at altitudes less than 1,000 feet when the aircraft is climbing. No traffic advisories are issued when the intruder altitude is less than 380 feet. No aural advisories are issued at altitudes less than 400 feet when the aircraft is descending, and for altitudes less than 600 feet when the aircraft is climbing. Lightning Sensor System. The lightning sensor system detects and locates areas of lightning activity in a 200 nautical mile radius around the airplane. The system displays lightning rate of occurrence and position relative to the airplane. The Weather Radar Virtual Controller includes the LSS operating modes. LX mode activates the LX mode on and off. LX clear. Past strikes and symbols are cleared. When pushed, after 3 seconds the equipment enters the pilot-activated self-test mode. Lightning Sensor System Symbols. 1. Rate of occurrence symbols. Lightning rate symbols and their location represent the lightning rate of occurrence for the last 2 minutes. Rate 1 represents a single strike. Rate 2 represents 3 strikes. Rate 3 represents 6 or more lightning strikes. 2. Alert symbol. Lightning activity that only provides bearing information is displayed as a magenta alert symbol for 5 seconds. Radio Navigation System. The Primus Epic radio system on board the airplane comprises the standard navigation functions including Very High Frequency Omnidirectional Range, VOR, Automatic Direction Finder, ADF, Distance Measuring Equipment, DME, Instrument Landing System, ILS, and Air Traffic Control, ATC transponder systems. The radio navigation system utilizes system modules housed in 2 remote-mounted modular radio cabinets. The DC Essential Bus 1 powers the MRC-1, while the DC Bus 2 via SPDA-2 powers the MRC-2. The MCDU is the primary means of selecting and tuning the navigation radios. A secondary means of radio control is accomplished using the CCD and the PFD. Radio Navigation System. The Primus Epic radio system on board the airplane comprises the standard navigation functions including Very High Frequency Omnidirectional Range, VOR, Automatic Direction Finder, ADF, Distance Measuring Equipment, DME, Instrument Landing System, ILS, and Air Traffic Control, ATC transponder systems. The radio navigation system utilizes system modules housed in 2 remote-mounted modular radio cabinets. The DC Essential Bus 1 powers the MRC-1, while the DC Bus 2 via SPDA-2 powers the MRC-2. The MCDU is the primary means of selecting and tuning the navigation radios. A secondary means of radio control is accomplished using the CCD and the PFD. The Distance Measuring Equipment System, DME, is an integrated part of the Epic Avionics Suite. The DME system enables en route and terminal navigation and area guidance. The DME is capable of tracking 4 channels to provide slant range, time to station, station identification, and ground speed. Frequency tuning is automatically paired with VHF nav. The DME can also operate in the hold-on mode, in which case the frequency is not paired with VHF nav. When only one DME is installed, one station ident channel is for the captain's active frequency and the other for the co-pilot's active frequency. The DME system consists of DME module and a DME antenna. A second is optional. The DME interfaces with the display system and FMS through the ASCB D-bus. Press the Nav button on the MCDU to go to Nav page 1 of 1. Press the line select key next to DME to cycle DME hold on or off. The transponder system is an integrated part of the EPIC Avionics suite. Transponder, XPDR. A Mode S transponder is installed in MRC1 and MRC2. Each transponder provides both conventional and enhanced ATC functions. Press the radio button on the MCDU to go to radio page 1 of 2. On radio page 1 of 2, it is possible to enter the transponder code. This can be accomplished using the tuning knob or the numeric buttons. The Automatic Direction Finder system is an integrated part of the EPIC Avionics suite. The ADF module enables en route and terminal navigational and area guidance. The ADF has two selectable bandwidths, a narrowband mode to reduce noise during navigation use, and a wideband mode to improve clarity when listening to voice signals. The selectable modes are antenna, ADF, and beat frequency oscillator. ADF audio is transmitted from the digital audio bus to each audio panel in the system. Press the radio button on the MCDU to go to radio page 1 of 2. Press Next button on MCDU to go to radio page 2 of 2. On radio page 2 of 2 is possible to tune and activate the ADF frequency. The tuning can be accomplished using the tuning knob or the numeric buttons. Press the respective standby frequency line select key twice, if not boxed. Otherwise, press once to go to ADF page 1 of 1. On the ADF page, it is possible to capture a frequency tuned in memory. Press the respective line select key to box the stored tune and use the tuning knob to cycle the stored frequencies. Press the active frequency to capture the selected stored tune. The Global Positioning System, GPS, is a baseline system on board the airplane, and a second GPS is optional. The GPS module is a satellite navigation sensor, which uses the Standard Positioning Service, SPS, from Navstar GPS, Global Positioning System satellites. The baseline GPS module is contained within MAU-1 in the forward fuselage avionics bay. If the optional second GPS is installed, it is contained in MAU-3 in the center fuselage avionics bay. The GPS module receives satellite signals from an active antenna in order to compute airplane position, velocity, and time. The GPS interfaces are the clock, the optional ELT navigation unit, the IRS, the EGPWS, the FMS, the CMC, and the master warning function receives signals to display the GPS CAS messages. The GPS module has no direct interface with the flight crew. All device input data will come from other systems, and all output data will be routed to other systems. These other systems will be responsible for the display of output data and for providing input data. Any faults within the GPS will be reported on the multifunction control display unit, and the message indicator on the PFD will illuminate. When the GPS has lost integrity, GPS RAIM above limits is displayed on the MCDU. When the integrity exceeds the limit, a RAIM will exceed limit is displayed, and when RAIM, Receiver Autonomous Integrity Monitor, is not available, GPS RAME unavailable is shown. The Flight Management System, FMS, manages navigation sensors to produce the airplane position. The system provides data for the cockpit displays and flight control system. The FMS serves as an aid to flight planning, navigation, performance, and database and redundancy management. The system may be installed in a single or dual configuration. Should the airplane have a dual configuration, each unit can provide navigation data to the other unit. The FMS1 function resides on the NIC processor module in MAU2, in the forward electronics bay, and receives power from DC bus 2. The FMS2, in a dual installation, resides on the NIC processor module in MAU3, in the center electronics bay, and receives power from DC Essential Bus 2. The FMS is mainly composed of the following components: 2 multifunction control display units, 1 data management unit, optional, MAU hardware, 2 processor modules with FMS software, 1 database module. The FMS interfaces with the following systems and equipment. GPS. The FMS uses inputs from the GPS to calculate aircraft position and perform navigation functions. IRS. The FMS uses inputs from the IRS to obtain aircraft position and perform navigation functions. MFD and PFD. The FMS provides data for display navigation guidance on the PFD and navigation map data on the MFD. ADF. The FMS uses inputs from the ADF to perform navigation functions. The Multifunction Control Display Unit, MCDU, located on the control pedestal, provides control functions management and operating modes for proper FMS operation. It is the interface between the FMS and the flight crew. Flight planning. In general, flight plans may be divided into 4 categories: active, stored, lateral, or vertical. Active flight plan. This is the flight plan currently being flown. The active flight plan can be entered waypoint by waypoint, loaded from an external source, or recalled from storage. At a minimum, active flight plans must contain a from waypoint, possibly the origin, a to waypoint, and a destination. A flight plan is considered closed when the last waypoint is the destination. Stored flight plan. The flight plan is said to be stored when it is saved in the computer's memory and can be recalled later and made the active flight plan. When entering a flight plan to store, the flight plan must have an origin and destination waypoint, and both must be database waypoints. When recalling a flight plan, entering the name of the flight plan results in the flight plan becoming active. If the name of the flight plan cannot be found, the flight crew can enter the origin and destination. If any are found, the flight plan list page is displayed to allow selection of a flight plan. Lateral flight plan. The lateral flight plan begins at the origin. The default origin in the active flight plan is the nearest airport to the present aircraft position that is within 3 miles, but it may be changed by the flight crew. The flight plan ends at the destination, which must be entered by the pilot as there is no default destination. The flight plan is built by inserting waypoints or strings of waypoints between the origin and destination. Examples of strings of waypoints are Standard Instrument Departure Procedures, SID, Airways, Standard Terminal Arrival Procedures, STARS, and Approach Transitions. Vertical Flight Plan. Vertical definitions for waypoints can be made using the line select keys on the right side of the flight plan pages. No vertical entries are required to operate the Vertical Navigation Mode, VNAV. The FMS supplies predicted information for each waypoint, which is sufficient to define the vertical profile. The following information is displayed and/or entered for each waypoint in the flight plan, such as altitude, speed, angle, vertical speed, constraint type. Database. The FMS has 3 databases in its memory: a navigation database, a custom database, and an aircraft database. Navigation database. This database contains data on nav aids, airports, and airways. The information in the navigation database is updated every 28 days. The database contains 2 consecutive effectivity cycles, and the correct database may be automatically or manually selected. Automatic selection occurs upon entry of a valid date. Dates are valid if they are greater than or equal to the expiration date of the current cycle. Custom database. The custom database contains information entered by the pilot. This is where the pilot can create and store flight plans and waypoints. This database is not updated on a scheduled basis. Aircraft database. The aircraft database contains all aircraft-specific performance parameters. After each flight, all learned data is saved to the file automatically. Therefore, all performance data, learned and fixed, is contained in the file. Performance. This function gives access to performance-related pages, including performance initialization, climb, cruise, descent, wind, fuel management, and takeoff and landing data. In addition, permits the initialization of stored flight plans and execute performance computations. Navigation. This function gives access to index providing access to position sensor data, stored flight plans, fix info, selection of waypoints and maintenance pages. In addition, in this page it is possible to perform data loading using a remote terminal or DMU. Flight plan. This function provides flight plan data for each leg in the planned, active flight plan including course, distance, and FPA altitude constraints. It is also possible to create a flight plan, select a stored flight plan, and load a flight plan from a disk. Progress. This function summarizes important dynamic flight parameters and the airplane relationship with the active flight plan, such as estimated time en route, distance to go, fuel information, current nav mode, number of long-range navs used, nav aids that are presently tuned, FMS navigation mode, closest nav aids, and air data information, current speed, altitude, and temperature. Route, RTE. This function inserts the following prompts on the active flight plan pages: direct, pattern, and intercept. FMS controls and indicators. Multifunction Control Display Unit, MCDU. The MCDUs are installed on the central console located next to each crew member seat and are easily accessible and readable. Line Select buttons. There are two line select keys on the MCDU to select FMS functions. They are used in conjunction with the alphanumeric buttons. FMS symbology on PFD. The FMS button on Display Controller selects FMS as the primary navigation source and toggles between FMS sources. FMS symbology on MFD. The FMS button on Display Controller selects FMS as the primary navigation source and toggles between FMS sources. Vertical Profile on Map or Plan menus selects vertical profile flight path data for display. Progress on Map or Plan menus selects flight progress data for display. The following fault messages can be displayed on the ICUS.